Assalamualaikum and hello everyone. I am Ani Shazwadimiti Apandi and I am the leader for the group for this week, which is experiment 4, minor losses in pipe.
So, hi everyone. Today I'm going to talk about the abstract of this experiment. So, by the way, I'm Datuk Z. So, this experiment is to examine the loss coefficient value, which is the KL, and the HLM, which is the minor head loss in pipes for different water flow rates, pipe diameters, and also pipe bends. In this experiment, there are a few types of pipe section that will be used, include sudden enlargement and sudden contraction, and also not to forget the bends and the branches. So the value of KL for the fluid flows through a sudden expansion and contraction can be obtained by considering the continuity, momentum, and energy equation between points 1 and 2 for the control volume. The value of minor loss, the HLM for the flows involving pipe components, or known as the fittings, such as elbows, pipe bends, and pipe branches, could be determined experimentally using equation. For the value of KL, it can be determined using typical values of KL for pipe components. At the end of this experiment, effects of different water flow rates, pipe diameter, and pipe bends on the value of the loss coefficient will be discussed. Thank you.
Okay, so these are the objective. The first one is to determine loss coefficient or KL value and minor head losses for different water flow rates. Second one is to determine loss coefficient and minor head losses for different pipe diameters. And then the last one is to determine loss coefficient and minor head losses for different pipe bends.
Now I will present about the introduction. As an incompressible fluid flow through a pipe, friction forces along the pipe wall is created against the flow, which generate a continuous loss of energy in the fluid and decrease the pressure of the fluid. So there are 4 factors that can determine the friction losses in pipe. The first one is velocity of the fluid, internal diameter of the pipe, direction of flow in the pipe, and last but not least is the length of the pipe. Furthermore, there are always head losses in pipes due to an enlargement or contraction of the flow section, bends, junctions, and valves, which known as minor losses. When the direction of flow is altered, the energy losses occur which are not recovered, will dissipated in eddies, and turbulence occur, which finally lost in the form of heat. However, in the long pipelines, the effect of minor losses may be negligible, while for short pipelines, the losses may be greater than the friction.
So this is the theory. Next. Okay, these are the theory. There are total 10 equation, and then as we can see, we use a lot of formula over here, and there are some definition for each formula. Okay, next. Okay, for the for the KL, this equation can be arranged to give theoretical KL for sudden expansion or enlargement, and there are the details for the theory. Next, please. Okay, this is the figure this is the figure for the KL for pipe components for each pipe bend. Okay, we have elbows, and then 180-degree return bands, T's, and union threaded, and also valves.
Hi everyone, I'm Ko Yong Khan and I'll present the methodology. So now let us see through the apparatus first. This is a pressure measurement test bench, and you can see the test pipe station, inlet and outlet web, 2 tube manometer and manometer tube. So you can see to the detailed part of the test pipe station. So first you can see the 2 tube manometer at the left side. Next, we'll come to the inlet web. Then we can look through the pipe we are going to test. The first one is sudden enlargement tube, the sudden contraction pipe, the Y-type pipe, E-type, the angle 90 degree, the bend 90 degree, And the last one, angle 45 degrees. And also the outlet west. So we'll come into the procedure. So first, the direction of water inflow and outflow are determined for the test pipe station. So you can see the T-type test pipe. The flow direction is determined by the yellow arrow. So next, the inlet valve of test pipe station is fully open. So we are turning it anti-clockwise direction. This is all the inlet valves we are going to open. Next, the main switch and pump is turned on. So after turn on the pump, we are the inlet valve H1 and the outlet flowing pressure H2 for the test pipe station is identified and the manometer tube is connected. So the value of H1 and H2 will be recorded in unit millimeter. So next, the actual water flow rate is determined by recording the time taken to collect 3 liters of water at the tank. After that, the opening of outlet valve is reduced by turning it clockwise for second reading of experiment. So the value of H1 and H2 at 2 cube manometer is recorded again. Again, the actual water flow rate is determined. After that, the opening of outlet valve is reduced and the step 8 and 9 is repeated for another 3 different values of actual flow rate. After finish, the manometer tube is removed first to avoid the bubbles in the tube. With pump in running condition, steps 1 to 11 is repeated for the other test pipe station. So after finish, all the manometer tube is removed from the system. The inlet and outlet valve is fully closed, and the pump and the main switch are turned off. So the experiment ends. Thank you.
Now I will present about the results of the experiment. So table 1 shows the data for sudden enlargement and sudden contraction. So the first thing that we need to do is find the actual flow rate and the differences in height. And then we need to calculate the average actual flow rate for both of the pipe, which is for sudden enlargement and sudden contraction. So for sudden enlargement, we got the average of actual flow rate is 0.0233 meter cube per minute. And for sudden contraction, we got 0.0233 meter cube per minute. Next is table 2, which is the data for pipe elbows. There are 3 elbows here, which is 90-degree angle, 90-degree bend, and 45-degree angle. So it's same method as table 1 just now, which is we need to find the actual flow rate and differences in height. And then we need to find the average of actual flow rate for these 3 elbows. So for 90-degree angle pipe, we got 0.0216 meter cube per minute. For 90-degree bend pipe, we got 0.0184 meter cube per minute. And for 45-degree angle pipe, we got 0.0216 meter cube per minute. Next is for table 3, which is the data for pipe branches. We have 2 types of branches here, which is Y-type and T-type. So the first thing we need to find is actual flow rate and differences in height from the given data. And then we need to find the average of actual flow rate of Y-type and T-type. So for Y-type pipe, we got the average flow rate is 0.0187 meter cube per minute. And for T-type pipe, we got 0.0229 meter cube per minute. Next will be the discussion. So the first question of the discussion is calculate the minor head loss and loss coefficient for each of the pipe components or fittings. So the first one is sudden enlargement. At the left side of the slide in the box is the given data. And then the first thing that we need to do is find the internal diameter of diameter 1 and diameter 2. And then we need to find the area 1 and area 2 in order for us to get the loss coefficient. So for sudden enlargement, we got the loss coefficient is 0.41. Next, we need to find the velocity as well as the minor losses from the given data in the box at the left side. So we got the velocity 102.7 meter per minute. And for minor losses, we got 0.06122 meter. Next is the sudden contraction. So we use the same method as sudden enlargement just now, which is the first one is we need to find the internal diameter for diameter 1 and diameter 2, and then area 1 and area 2 in order for us to get the loss coefficient. So loss coefficient for sudden contraction is 0.41. Next, we need to find the velocity and minor losses of sudden contraction. So what we do is just substitute the data in the box there into the velocity equation and minor losses equation, and then we got the velocity 102.7 meter per minute and minor losses 0.02389 meter. Alright, next will be 90-degree angle pipe. So the first thing that we need to find is internal diameter, which is 70 millimeter, and then we need to find the loss coefficient, which is 1.5. We got this value from figure 3 from the laboratory manual. And then we need to find the velocity and also the minor losses of 90-degree angle pipe. So for the velocity, we got 95.163 meter per minute, and for minor losses, we got 0.1923 meter. Next will be the 45-degree angle pipe. So seems like 90-degree angle pipe just now. First, we need to find the internal diameter, which is 17 millimeter, and then we need to find the loss coefficient. For this loss coefficient, we got it from figure 3 in the laboratory manual. At the bottom one is regular 45-degree threaded. So we got 0.4. Next, we need to find the velocity and minor losses. So for the velocity, we got 95.163 meter per minute, and for minor losses, we got 0.05129 meter. Next will be the 90-degree bend pipe. So the first thing we need to find the internal diameter, which is 17 mm, and then we need to find the loss coefficient. So for the loss coefficient, we got it from figure 3 here, which a long radius 90-degree threaded, which is 0.7. Next, we need to find the velocity and minor losses. So for velocity, we got 81.064 meter per minute, and for minor losses, we got 0.06513 meter. Alright, next will be the T-type pipe. This is the first type for the branches. So the first thing that we need to find is the internal diameter, which is we got 17 mm, and then we need to find the loss coefficient. We got 2.0 from the figure 3 here. In this category, we got branches flow threaded, which is 2.0. And then we need to find the velocity and minor losses. For velocity, we got 100.89 meter per minute, and for minor losses, we got 0.2882 meter. Alright, so last but not least is Y-type pipe. So the first thing that we need to find is internal diameter, which is we got 17 millimeter, and then we need to find the loss coefficient, which is we got 2.0. Next, we need to find the velocity and minor losses. So for the velocity, we got 82.386 meter per minute, and for minor losses, we got 0.1922 meter. Alright, next will be the second question of the discussion, which is the effects of different water flow rates, pipe diameters, and pipe bends on the value of loss coefficient. The first one is losses in pipe depends on the diameter of the pipe. What is the relationship? How does it work, right? So the smaller the diameter, the more friction it will contain and more energy will lost. Thus, the higher the loss coefficient. Next, losses in pipe are also dependent on the flow rate. If the flow rate is high, the friction loss in pipe is greater. Thus, the loss coefficient will be higher. The last one is losses in pipe depends on the pipe bends. The longer the bending of the pipe, the more the gradual turn of the bends, thus the lower the loss coefficient. Alright, so for the last question of the discussion, factors contributing to errors and inaccuracy in experimental data and the possible recommendations to improve the existing results. So for the factors that are contributing to the errors, first is presence of air bubbles in the tube as well as in the pipe, parallax error due to the incorrect position of the eye to the scale, and last one is water level in 2-tube manometer cannot be calibrated, then it fluctuates heavily. Next will be the possible recommendation to improve the existing results. So the first one is make sure no air bubble trapped in the tube or pipes. Second one, make sure the position of the eye is perpendicular to the reading scale. And last one is adjust the volumetric flow until it do not fluctuate or take the average of the reading. Alright, so that's all for the results and the discussion. Thank you.
So now I'm going to talk about the conclusion and recommendation of this experiment. So let's focus on the conclusion first. The conclusion of this experiment is to determine the loss coefficient and the minor head loss in the pipe. The component in the pipe components or the fittings for different water flow rates, pipe diameters, and also pipe bend. For bends, the lower the K value for a bend, the smoother it is, and the opposite is true for a high K value bend. Thank you. Now the recommendation of this experiment, we have a lot of things to say. So mainly we focus on this 7 recommendation. The first one is the position of the eyes must be perpendicular to the scale of meniscus to avoid parallax error. Second, we need to repeat the experiment at least 3 times for each reading to get a true value by finding its average. And we also need to make sure the environment is in safe condition and under control to avoid any systematic error. And also the data must be recorded carefully and neatly so that we can avoid any human error during the calculation so that we can get an accurate result. And then also we need to use the equality equipment to be paramount by reducing systematic measurement error by using an updated and precise measuring device that doesn't have any defects. And last but not least, we need to conduct the experiment step by step according to the methodology in order to make sure the result obtained is accurate. Thank you.
Last but not least is the references. So these are the 3 references that we're using in order for us to complete this report, which is for experiment 4, minor losses in pipe. If you have any question or you want to know more about the experiment, then you can refer from these references.